Hello, Precalculus folks. Welcome to your online lesson for Wednesday. This is 4.3 Exponential Functions. We're first going to start by reviewing the laws of exponents. Dun dun dun. So you have elements s, t, a, and b. They're all elements of the real numbers. A and b are greater than 0. So the first rule that I want to talk about is the product rule. If you have a to the s times a to the t, meaning their bases are the same, you basically add the exponents. If you forget this, I recommend writing out and expanding some example that you're really familiar with, such as x to the second times x to the third. What do? X times x times x times x times x, that's x to the fifth, right? Same goes now if you suppose have x to the second and all of that is raised to the third power. Well, by expanding, you have x to the second times x to the second times x to the second. That leaves you with x to the sixth. And if you wanted to, you could write it out, if you forgot, to add those exponents, 2 plus 2 plus 2. You're adding 2 3 times, or you can think of it as multiplication. X to the 2 raised to the third power is x to the 2 times 3, so we're multiplying there. Okay, so we're going to start off with an example that I'd like to show you. This is just some relationship from an input and an output. F is our function. And it looks like every input gets, or every output is doubled. So if you take f of 0, which is equal to 3, right, and you multiply it by 2, that gives you f of 1. Does everybody see that? So if you do the next one, what do you do with that 3 times 2, or the 6? You multiply it by 2. So I'm taking the previous term, f of 1, multiplying it by 2 again, and that leaves me with 12. So 3 times 2 is f of 1 times another 2. That ends up with 3 times 2 to the second. Notice I'm not expanding, I'm just looking for a pattern. With the next one, I'm going to take f of 2. Oh yes, and you fill in 3 times 2 to the 0. With x equals 3, if you take the previous input, f of 2, multiply that by 2, that will land you at 24, which is 3 times 2 to the second times 2 again. How many 2's is that? That's 3 times 2 to the third. Anybody noticing a pattern? So we're going to take f of 3, multiply that by 2, take the previous number, 3 times 2 to the third, multiply that by another 2. That leaves you with 3 times 2 to the fourth. Beautiful, isn't it? So what about ... for any value, n? So where does that land you? What's the rule going to be? 3 times 2 to the n, right? So we can extend this to the definition of what an exponential function is. Just keep in mind that 3 is what's known as your initial value, and 2 is what's called the growth factor. If you compare the ratio of the two consecutive terms, f of 3 over f of 2, look what happens. You're left with 2. That is what's known as the growth factor. I'm multiplying every term by 2 to get to the next one. And not equal 1, that wouldn't be a very exciting exponential function. C is not equal to 0, and C is an element. So here's the definition of an exponential function. Some function, c a to the x, where a is an element of the reals, a cannot equal 1. Wouldn't be a very exciting function, would it? C not equal to 0, and C is an element of the reals. The domain is all real numbers, which is great. A is the growth factor, which we talked about before, and the initial value, it's when x is equal to 0. So c a to the 0, once again, that would be c times a to the first, or c times 1, which is equal to c. So that's the initial value. That comes up a lot in application problems. So from our initial example, we have 3 as our initial value, and you can check that by inputting f of 0. You get 2 to the 0 is 1, so it's 3. 2 is our growth factor. We're doubling every output from the previous output. So we have a theorem that to find the growth factor, you take the ratio of the 2 consecutive terms, f of x plus 1 over f of x, which is equal to a. So, look at 3 examples from the book. The instructions for this are So looking at 3 examples in the book, the instructions say determine whether the given function is linear, exponential, or neither. For those that are linear functions, find a linear function that models the data. For those that are exponential, find an exponential function that models the data. So we're going to start with number 26. This ends up being a linear relationship. And you can see that to get from 2 to 5, you add 3. From 5 to 8, you add 3, adding 3 from 8 to 11, and 3 from 11 to 14. You've got to check your x's, make sure that the change in x is also increasing by 1. So therefore the change in y over the change in x is equal to 3 over 1. And that is, in fact, the slope. That's a linear relationship. And if you see there, that's our y-intercept, which is b, 5. So our equation is 3x plus 5. Now looking at number 32, if I take the difference from 1/2 to 1/4, I have to subtract a fourth. Then I'm subtracting an eighth. So you can see that this is not linear. So you can stop with that. And now we're going to check if it's an exponential by checking the ratio of the 2 consecutive terms. So we're going to compare 1/4 over 1/2. If you simplify that, you end up with 1/2. 1/8 over 1/4 will also give you 1/2. 1/16 over 1/8 will give you 1/2. So you can see that this is our growth factor for our exponential function. So we'll write that down. Now we need to think about the initial value, c. Remember, the initial value is for the input x equals 0. So what is that initial value going to be? It's going to be c equals 1/4. So you put it all together using the definition of an exponential function, and your f of x is going to equal 1/4 times 1/2 raised to the x power. So we're going to check a few values just to make sure that we have this written down correctly. So let's try f of 3. So 1/4 times 1/2 raised to the 3rd power. Using the laws of exponents, that's 1 goes to the 3 and to the 2, which is 1 over 4 times 8. 1 over 32. That checks. So we know that this is a good function rule. So this is like example 2. Number 30 we're going to look at, and this actually ends up being neither, the relationship. So the difference from 6 to 1 is -5. Now it's -1. Now the difference from 0 to 3 is 3. So comparing these, you can see that there is actually no relationship here. And comparing the consecutive terms, their ratio, we don't have anything consistent. So this is neither. Now we're going to graph an exponential function. This is like example 3 in your textbook. So suppose we graph f of x is equal to 3 to the x. So what I'm going to do is I'm going to get a table of values. Here's x and here's f of x equals 3 to the x. And so now what we're going to do, I'm just going to get a different pen color. Let's do some negative values like negative 10. So what does that mean? 3 to the negative 10. Well, 1 over 3 to the 10th. That's 3 times 3 times 3 times 3 times 3. That's 10 times. That's a really big number, right? So we can say that that's getting really close to, but not quite 0, right? Let's look at a more reasonable number like negative 3. So 3 to the negative third is equal to 1 over 3 cubed, which is 1 over 27. And then negative 2, so we're just going to do a bunch of values. 3 to the negative 2 is 1 over 3 squared, which is 1/9. Negative 1, 3 to the negative 1, 1 over 3 to the 1, which is equal to 1/3. Going to extend this line. Let's do 2. What is 2? Well, that's 3 squared. So that's 9. 3, that's 3 cubed, which is 27. And just for fun, think about what 3 to the 10th might be. That's excuse me, what 10 would be. So 3 to the 10th. That's going to be a really big number. You can calculate it if you want to, but that's the idea. Just for fun, let's do that. Here we go. You guys can see that, right? So let's do 3 to the 10th. That's a pretty big number, right? So when you're thinking about this graphically, let's just do, since we're doing this, 1 divided by, whoopsies, 1 divided by 3 to the 10th. You see how the e to the negative 5, that means you move the decimal over 5 places to the left. So we're going to move it 5 places to the left. So that's a really small number, like we said. Okay, so now if we're looking at the graph of this, we already said that an exponential function, the domain is all real numbers, right? And a couple of important features. Oh, I left out the most important number. Do you see which number? I left out, if we continue our chart, x and f of x, 0. What is 3 to the 0? 1. That tells me that regardless of any exponential function, that as long as there isn't an initial value out front, you're going to have it's going to go through 1. So it's going, let's see, let's just plot some points, like negative 1 is at 1/3, so here, and then I'm going to show that's 0, 1, and here's 1/3, and here's negative 2 is 1/9, and then negative 3 is 1/27. Do you see that we're getting really, really close? And then 4, 5, 6, 7, 8. That's a number that's even closer to 0. So the end behavior as x approaches negative infinity is that the function f of x is going to approach 0. It's kind of like a horizontal asymptote towards the left. On the right-hand side, what's happening to this exponential? Well, at x equals, looks like I don't even have 2, but if you did x equals 1, 3 to the first power is 3, right? So you go up 1, 2, 3. So 1, 3 is a point. And it's always good to label a couple of these. And then 2, we said that 3 to the second is 9. So we've got 3, 4, 5, 6, 7, 8, 9. So that's way up here. We couldn't even put 10 on here. That number is way too big. So, and you've probably seen this exponential curve, which I didn't do so nicely, but it curves and it increases rapidly beyond or for positive values of x. Now, keep in mind that this is when your base is greater than 1. So a is greater than 1. That's also, remember, your growth factor. Okay? So we're going to look at the case now where a is between 0 and 1. Okay, so now we're going to graph a particular case where the growth factor, which is 1/3, is greater than 0, which your base has to be greater than 0, but less than 1. So there, something different happens, and let's go by just starting with finding some values. So -10, once again, if you raise 1/3 to the -10, well, that's the same as 3 over 1 to the +10, which is equivalent to 3 to the 10. Does that look familiar? Or 3 to the 10th power. Now let's try something smaller, -3. So that's 1/3 to the -3, which is equivalent to 3 over 1 to the 3rd, which is 3 to the 3rd, which is 27. Okay? Continuing on, let's do -1. 1/3, -1, that switches the quotient. It becomes the reciprocal, so that's 3 over 1 to the +1, or just 3. 0, anything to the 0 power is still just 1. So 1/3 to the 0 power is 1. 1, let's see, what is 1/3 to the first power? That's just 1/3. 2, that's 1/3 to the second power, which is 1 over 3 squared, which is 1/9. Now, as we get bigger, what's happening? We have 1/3 to the 3rd power is equal to 1 over 3 to the 3rd, which is 1 over 27. So, as the numbers increase, like down to 10, do you see how the outputs are getting smaller and smaller this time? That's a 10. So it's 1 over 3 to the 10th power, which is a really small number. Okay? This right here is a really big number, right? So let's spice this up and get a different color for our graph. I'll draw the axes like this first. Here we go. Here's my beautiful graph. Curves included, even though those are supposed to be straight lines. Trust me. Let's do some pink. Okay, so we're going to graph. -10 I can't really graph. It's going to be way, way off the charts, but very positive, and it's going to be in the second quadrant. If we graph -3, so 1, 2, 3, that's 27. That's going to be way up here. Let's just say that that's right here. -3, graph not to scale, 27 is right here. Now if we graph -1, we're at 3. So here's 1, 2, 3, -1, 3. And if we graph 0, we're at 1. If we graph 2 or 1, we're at 1/3. And 2 is going to get even closer to the x-axis, which is 1/9. 3 is going to be down to 1/27. Do you guys see what's going on? It's just reflected about the y-axis. So now, if your growth factor is between 0 and 1, I'm not doing this justice. Look at the book, please, to get a better example. But the idea is if your growth factor is between 0 and 1, your function is decreasing from left to right. Okay? Whereas if your growth factor is greater than 1, your function is increasing from left to right. So I summarized that in properties here. Let's first look at the properties from 0 to 1. If the base is between 0 and 1. That's also the growth factor. So the domain is a set of all real numbers, or negative infinity to positive infinity. And the range is the set of all positive reals. So check that out. It should be positive real numbers here. Keep that in mind, from 0 to infinity. That's the y values. There are no x-intercepts. The y-intercept is 1. Okay, and we agree that's the point 0, 1, remember? The x-axis is y equals 0. The horizontal asymptote as x approaches positive infinity, not negative infinity, is 0. That's one way to write it, y equals 0. And f of x, it's a decreasing function, and it is 1-to-1. That means it's an inverse, and we're going to talk about that more on Friday with logarithms. And the graph of f contains the points -1, 1 over a, 0, 1, which it has in both, and 1a. The graph of f is smooth and continuous with no corners and no gaps. Okay? As far as properties of exponential function for a growth factor or a base that's greater than 1. Similar stuff. The domain is the set of all real numbers, and the range, once again, is all positive real numbers. Just try to get a negative output. Just try it. I challenge you. There are no x-intercepts. Once again, the y-intercept is 1. The x-axis, y equals 0, is the horizontal asymptote, but in this case, it's as x approaches negative infinity, and you can write it like this: the limit as x approaches negative infinity of your exponential function a to x. The x is equal to 0. It's increasing from left to right. It's an increasing function, and it is 1-to-1. And it contains the points 0, 1, 1a, and -1, 1 over a. The graph is also smooth and continuous. So remember, this graph looks like this, increasing. Okay, we're going to try number 47, which is similar to example 5. It says graph the function 3 to the negative x minus 2 using transformations and find the domain, range, and horizontal asymptotes. So what I want to point out is this negative right here. If you remember, that's on the inside. That's affecting the x. So that's the flip about the y-axis, believe it or not. And this -2 tells me to go down 2 units. Let me just show you something, though, if you wanted to think of it. The reason why you're flipping it about the y-axis, you start out with something we said just recently with if your base is greater than 1, it's going to be increasing, right? Now, this is for a greater than 1. And if a is between 0 and 1, then the exponential function is going to be decreasing from left to right. They both go through 0, 1. We talked about that, and that's important to know. 0, 1, and 0, 1 here. But, so it looks like y would, if it flips about the y-axis, then that's going to be a decreasing function from left to right, right? But think about 3 to the negative x. What's 3 to the negative x? 3 to the negative x is 1 over 3 to the x, right? And you could just rewrite this because 1 to anything is just 1. So this is the same as 1/3 to the x power, right? So that really is thinking about a function whose base is between 0 and 1. Okay, so I want you to keep that in mind. And then you just go down 2 units. So if we sketch this, rather than being at 0, 1, I'm going to shift my graph down 2 units. So here's 0, 1, but that's not a point on the graph. I'm going down. Here's 0, 0, and here's 0, -1. Okay? Rather than going up like we would for 3 to the x, and you can see then that your horizontal asymptote would be this line. If you shift it, it originally is at y equals 0, right? But now it's at y equals -2. So I'm going to draw this in pink. So what I would say is now it's reflected about the y-axis, so now it's going to be increasing up, and as x approaches positive infinity, my exponential function is approaching this horizontal asymptote, -2. So thinking about domain, well, the domain is just all real numbers. What about the range? Well, the range is all y values that are greater than or equal to, not equal to, erase that, that's bad. So you can see it, just strictly greater than -2. Okay, so y is greater than -2. So those domain and range, and then you can say you have a horizontal asymptote. Basically, if we wanted to write it in limit form, it's the limit as x approaches positive infinity, in this case, of our function f of x equals 0. You can also just say horizontal asymptote at y equals 0. I just wanted to show you that. And to also note that it's in the positive direction. Alright, so you thought that pi was the only special irrational number, right? Well, pi is old school now because we've got another irrational number. It's e, and this is often occurs in nature, this e, and where you find it is in exponential functions, and it's the base of an exponential function. So there's one way of approximating e. The number e is defined as the number that the expression up here, 1 plus 1 over n to the nth, as n approaches infinity, we end up getting approximately some values in the between the 2 to 3 range, and I'm going to show you that. So that's the what e is defined to be, and it's a great model for population growth, exponential growth and decay, and many other things that we're going to actually be doing very soon. So stand by. As you can see, as basically n approaches infinity, the value of e is approximately 2.71828. Notice dot dot dot. There's no pattern. It's not repeating. So if you are asked about e and if you are on a number line, well, e is somewhere in between. Here's 2. Here's 3. It's right about here. Okay, so just something to think about. On your calculator, you can find e right above the natural log button. So it's you push ln, you get e to the 1, and let's just check our results. Okay, that is approximately 2.718. Let's look at the graph of e to the x. So we're going to clear these. And once again, you just type in e, and we're going to put in x, and I'm going to graph it. I'm in standard. So notice that this function is increasing, so e to the 0 is still equal to 1. The function f of x, e to the x, is increasing. And remember, that's because e is greater than 1, so I know it's an increasing function. And the domain of e to the x is all real numbers. And once again, the range is all y values that are greater than 0. And so the graph looks like this, and it's really hard to kind of find exact values for e, but just trust the process that it is an increasing function. If you type in 1 or input 1, you get e to the 1. That's around 2.718. So when you're graphing this, the only real point that you know is this 0, 1, right? And that you do know as x approaches negative infinity, the graph is approaching y equals 0, that horizontal asymptote, and for x greater than 0, the function is increasing at a rapid rate. So now we're going to graph f of x equals e to the x minus 1 plus 2 using transformations on e to the x. Okay, so remember that on the inside there's a minus 1, so that's going to take me right 1 unit, and this right here will shift it up 2 units. Okay, so this right 1 is going to affect that point 0, 1. So I would think about 0, 1 as your most important point. So you're at 0, 1, and remember this is increasing like that. That's our original guy. So this is e to the x, and now if I go right 1 unit, that lands me, instead of at 0, 1, that lands me at 1, 1. And instead of at 1, 1, that's right, I also have to go up 2 units. So now instead of 1, 1, I'm going up 1 more, another 1. So my new graph, and we'll just do this, the final graph in a different color, right here is going to be at 1, and then 1 plus 2 is 3. So at 1, 3. Now, if your original horizontal asymptote is at this y equals 0, right, as x approaches negative infinity, well then shifting it up is going to give me a horizontal asymptote at y equals 2. So that's really all you need for graphing. You could find the once again, you could find the y-intercept, but it still is going to be in terms of e. So f of 0 is equal to e to the 0 minus 1 plus 2. That's just 1 over e plus 2, right? Which is 1 divided by 2.718 plus 2. So it just is basically a little above. It tells me it's a little above 2 up here. You don't really need to get too precise with this. Just basically this kind of center point, 1, 3, where it's shifted, locate that and label your horizontal asymptote, and I'll be a happy teacher. So there, and then we're increasing. Okay, so that's how to graph an exponential function using transformations. So now that we've talked about exponential functions and their graphs and properties of exponential functions, how do you solve an exponential equation, which gets to the really interesting stuff. So this property up here is very important, and basically if you have an equation, this is an equation because it's two things equal to one another. See how the bases are the same. If a is raised to the u power on this side and a is raised to the v power on the right hand side, then it's apparent that their exponents should be equal, right? U to the v. So a simple equation number 62, 5 to the x is equal to 5 to the negative 6. What can we say? Well, then x should equal negative 6. Done! I solved that. Okay, let's look at number 68. So 68, if you look in your book, is 5 to the x plus 3 over 1 over 5. Now, so far, the bases aren't the same, right? I need to get this base to be the same as this base, right? Well, how do you do that? We use the law of exponents. So this is 5 to the first power, so I'm going to raise it to the top and write 5 to the negative 1. And on the left-hand side, I still have 5 to the x plus 3. So now, do you see that our bases are the same, therefore the exponents must be the same? X plus 3 is equal to negative 1. Subtract 3 from both sides, x is equal to negative 4. Done! Yay! Okay, let's look at number 69. So I'm going to, I gotta clear up a little space. So number 69, if you look in your book, is 3 to the x raised to the third power equals 9 to the x. Once again, the bases aren't the same, so you have to try to get the bases the same. Try to get bases the same. Okay, so we can do that because 9 is equivalent to 3 squared. So here we have 3x to the third equals 3 squared, all raised to the x power, right? So that's equivalent to 3x to the third equals 3 to the 2x. When you raise a power to a power, you multiply. It's not x squared. Be careful of that. So now we have x cubed is equal to 2x. So the exponents should be equal, right? How do you solve an equation like this? What did we do in chapter 3? We learned how to solve equations like this, polynomial equations. It's a third degree. So I'm going to think about it as trying to find the zeros. So bring that 2x over to the other side. Do you see that the greatest common factor is x? So now I'm left with x squared minus 2 equals 0. Using the zero product property, x can equal 0, or x squared minus 2 can equal 0. So x squared equals 2. Take the square root of both sides. X can equal plus or minus the square root of 2. And x can equal 0 from the other. So this is my solution. Okay, I know you're getting tired of listening to me, so we're almost done. I'm going to show a couple more examples. So with this one, I'm trying to solve this equation. Remember, these are equations. Once again, the bases, I need to consolidate my bases. That's what the property said. So on the left, it's okay as e to the x squared, but let's do some algebra manipulation here to get it all as 1. I just brought this 2e to the second up to the top and wrote negative 2. So now I can consolidate. That's just the product rule, which says you add, right, the exponents. So now I have my bases are the same. X squared equals 3x minus 2. That's the same as plus negative 2. What does this smell like? A quadratic. So x squared minus 3x plus 2 equals 0. Can we factor that? Yes, I think we can. X minus 2 and then x minus 1, right? How convenient. So that means that x is equal to 2 or 1. Okay? So number 81 gets a little trickier. I just wanted to show you guys that. Basically, it's saying, so if 4 to the x equals 7, what does 4 to the negative 2x equal? So you take this 4 to the negative 2x and you think about how can I get 4 to the x from that? Well, you have to remember your laws of exponents. So I'm going to rearrange this 4 to the x and I'm going to raise it to the negative 2 power. Check and make sure you understand that when you raise a power to a power, it's x times negative 2. You multiply, so that would be negative 2x, right? So I already know that since we know that it's given that 4 to the x is equal to 7, I'm going to substitute it in. So sub 7 in for 4 to the x. So that means that that's equal to 7 to the negative 2, which is equal to 1 over 7 squared, which is equal to 1/49. The end. Okay, I'll see you all on Friday. Thanks for watching the video. Hope it was helpful. All right, bye.